Turns out that the concept of electrical potential energy is so useful and widely used that the scientists decided to create a second unit known as electrical potential, or also known as the volt. And this describes the amount of energy required by a charge to be at a point in space. And this is given by the formula V equals E divided by Q, where E is the energy of the charge at that point in space, and Q is the charge, along with its sign. So example, 5 coulombs, or negative 5 coulombs. Now a situation would be, let's suppose we have a region in space with no charges. Then every single point would have a voltage, or V, of 0. Since there's no charges around, if I brought another charge Q2 at this point, there's no forces acting on Q2, so there's no energy that I have to put in to bring Q2 at this point. So every single point in this region has voltage 0. If I have a positive charge sitting in this region, positive Q1, then every single region beside Q1 will have V that's greater than 0, and it's going to decrease the farther I get away. So decreasing potential. So it could be 50 over here, V equals 40 over here, V equals 50 over here, V equals 20 over here. These are all in volts. V equals 10 volts over here. And you'll notice from our formula, since V equals E divided by Q, E has units of joules, Q has units of coulombs, and so the voltage is equal to joules per coulomb. So this is the same thing as 40 joules per coulomb, 50 joules per coulomb, 20 joules per coulomb, etc. What this means is if I have a positive charge, Q3, that's very far away from Q1, so at a distance of approximately infinity, and its initial energy is 0, the amount of energy I'd have to put in to Q3 to bring it to this point over here, we can see that V equals E divided by Q, so then E is equal to Q times V, which is equal to Q3, let's say it's 2 coulombs, then 2 coulombs times 50 volts is equal to 2 coulombs times 50 joules per coulomb, which is 100 joules. So to bring Q3 to this point of potential 50 volts, I need 100 joules. Let's suppose that Q3 was, instead of 2 coulombs, it was 5 coulombs. Then now, let's say it was 5 coulombs. Then I'd need 5 coulombs times 50 volts. Which is now 250 joules to bring Q3 to this same point. Let's say Q3 was instead a negative charge, and it was negative 3 coulombs. Negative 3 coulombs. Then to bring Q3 to this same point in space of 50 volts, I need negative 150 joules of energy. So in other words, I don't even need to put in any energy to bring Q3 to Q1. It will go by itself. Now instead of having a positive charge in a region of space, let's suppose I have a negative charge in this region of space. So Q2. Then every single region in space beside Q2 is going to have a negative potential. V, so over here, let's say it's going to be negative 50 volts. Over here, negative 50 volts. Over here, negative 50 volts. The farther we get, it decreases in magnitude, but it increases in value. Because this is a negative charge, it's very similar to the electrical potential energy. So over here, we're going to have negative 30 volts. Over here, we'll have negative 10 volts. And once again, if I have another, let's say, positive charge, Q4 equals 10 coulombs, then to bring Q4 to this region in space of negative 50 volts, I'll need negative 50 times 10 coulombs, which is negative 500 joules. Let's say I have a negative charge, Q5 of negative 7 coulombs. Since this charge is negative, if I want to bring it to the same region, I'll need negative 50 times negative 7 coulombs, which would be negative, or positive this time, positive 350 joules. And so we're going back to that concept where two negative charges or two like charges have a positive potential energy between them, and two opposite charges, positive and negative, have a negative potential energy between them. And one last idea to be aware of is the region in space around a negative charge is called low potential, since it's negative, low potential. And if we had a positive charge, so Q1 again, then it would be high potential. Since it's positive. With this idea of electrical potential, we can understand the tendency of movement of charges a little bit better. So let's suppose we have a positive charge Q1, another positive charge Q2, and a third negative charge Q3. If I bring Q2 beside Q1, then the energy for Q2 is going to be Q2 times the potential at this region, V. Since Q1 is positive, then V is going to be a high potential region, and so V is positive, Q2 is positive, E2 is positive, greater than 0. Q3, if I bring it closer to Q1, E3 is going to be Q3 times V. Q3 is negative, V once again is positive, and so E3 is going to be negative times a positive, which is going to be a negative, less than 0. Now if we introduce a fourth negative charge into the mix, Q4, and I bring Q3 closer to Q4, then E3 to 4 is going to be Q3 times the second voltage at this region, but this is a negative charge, and so it's going to be a low potential region. Q3 is negative, V for this negative charge is also negative in the low potential region. Negative times negative is positive, and so this is a positive energy. If I move Q2 closer to Q4, then E24 is going to be Q2 times that voltage. Q2 is greater than 0, positive. V for this negative charge, again, low potential, is going to be negative. Positive times negative is less than 0. The golden rule is that all charges move to minimize their energy. And so in this situation, Q2 would go where its energy would be negative, so it would go towards Q4, and Q3 would go to where its energy would be negative, so towards Q1. So in general, negative charges tend to high potential and positive charges tend to low potential. Which is what you've probably already known, but now you have some intuition as to why. Now, another topic to be aware of is the concept of potential difference. Potential difference. So let's say I have two regions in space. First region being A, and a second region being B. And let's say there are charges in this region of space, we just can't see them. But they do have an influence on these 2 points. So at A, we have a potential VA, and at B, we have a potential VB. And let's say I have a charge already at A. So I have a charge Q at A, and I want to move it all the way to B. And I want to know the change of energy that will occur when I move this Q from A to B. A simple way to do that is look at the potential difference between A to B. So the potential difference is given by delta V, and it's equal to the second state. So in this case, we're going to be, there's our second state, minus the first state. In this case, we're going from A to B, so this is also known as delta V AB, where the first letter is where you're starting, the second letter is where you're ending. This is equal to VB minus VA. And it's also equal to the change in energy from point A to point B divided by the charge. And so the delta E that we're looking for, delta E, is equal to Q times delta VAB. We also know that delta E is equal to the work done by the electrical force, which is equal to the force times the displacement. And so delta V, which is equal to delta E divided by Q, is equal to the force times the displacement divided by Q. But we already know that the electrical force divided by a charge is equal to the field in that region. And so if we're dealing with a uniform electrical field, F divided by Q is going to be constant, and it's going to equal E. So this is equal to E delta D. So in other words, delta V is equal to E delta D, and the electrical field is equal in magnitude to delta V divided by delta D, which gives the electrical field units of volts per meter for uniform electric fields. So this is where your parallel plates would come in. So this units of volts per meter, let's look at that a bit closer. We have volts per meter. A volt is a joule per coulomb. So joule per coulomb meter. A joule is a Newton meter. So we essentially have Newton meters per coulomb meters, which is newtons per coulomb, which is what we had earlier, force per charge. And now we're ready for an example. So we have an electron traveling 6.2 times 10 to the 7 meters per second. That's launched from a positive plate traveling to a negative plate. The plates are parallel and are 10 centimeters apart and have a potential difference of 4.1 times 10 to the 5 volts between them. We want to know what the maximum distance that's traveled by the electron. So if we have our diagram, we have a positive plate and a negative plate. Since one's positive, one's negative, we have an electrical field going from the positive end to the negative end. We know that the total separation between the plates, which we'll call R, is 10 centimeters. And the magnitude of the potential difference between them, delta V magnitude, is equal to 4.1 times 10 to the 5 volts. And I say magnitude because we have to be careful about our reference here. If we go from the negative end to the positive end, we're going from low potential to high potential, and so we have an increase in potential, so that will give us a potential difference of positive 4.1 times 10 to the 5 volts. If we go from the positive end to the negative end, then we're going from high potential to low potential, which is a reduction in potential, and so we'll have a potential difference of negative 4.1 times 10 to the 5 volts. But in this case, we're going to deal with the sign by dealing with the situation and reasoning out how the electron is going to move. And so all we care about is actually the magnitude. So we have our electron, which is negative, and it has an initial velocity, v, equal to 6.2 times 10 to the 7 meters per second. And right now, since we know this E is negative, it has a negative charge, and this is a negative plate, we know the negative plate is going to repel the electron, so the electron is eventually going to turn around. There's a point where it has velocity 0, and we want to know what is the maximum displacement of the electron. And so right there, we dealt with the fact that the electron is negative and that the plate is negative, and so from now on, all we care about is the magnitude of the electron's charge and the magnitude of the potential difference. So, since this is a maximum displacement problem, we're going to resort to the idea of conservation of energy. So we'll call this our initial state, and where v is equal to 0, or where the maximum displacement occurs, we'll call that our second state. Since the electron is very small and is virtually weightless, we're going to assume that gravity is negligible. And what we have is ET1 is equal to ET2, or the initial kinetic energy plus the initial electrical potential energy is equal to EK2 plus EE2. But we just said at the second state that the velocity is 0, and so EK2 is equal to 0. And so EK1 is equal to EE2 minus EE1, which is the change in the electrical potential energy. And so all this is saying is that kinetic energy transforms to electrical potential energy throughout this process. Now, we're trying to solve for the maximum displacement, but I don't see that anywhere in our equation. What we can do is we know that the change in energy is equal to the work, in this case the electrical work, which is also equal to the force times the displacement, which is equal to, since this is a parallel plate scenario, the electrical field is uniform and the force is uniform. They're constant everywhere. We know that the electrical field is equal to F divided by Q, and so F is equal to Q times the electrical field. So EQ delta D. We still don't know what E is, but we saw previously that delta V is equal to E times delta D. In this case, we're given delta V for the entire separation between the two plates, and so our delta D also has to be the entire separation between the two plates. So instead of delta D, we're going to use R. And so E is simply equal to delta V divided by R. So be careful not to use the displacement of the electron, but the entire displacement between the two plates. And so what we get is that delta EE is equal to delta V times Q times delta D divided by r. And you can look at delta D divided by r as being the fraction of the distance traveled by the electron. So, going back to what we had, EK1 is equal to delta EE, so 1/2 mv squared is equal to delta VQ delta D divided by R. And so if we want to solve for delta D, it's equal to mv squared times R divided by 2 times delta V times Q. If we make our substitutions, m for an electron is 9.31 times 10 to the negative 31 kilograms. V is equal to our initial velocity of 6.2 times 10 to the 7 meters per second squared. Just going to erase this to make more room. Times R, which is equal to 10 centimeters, or 10 times 10 to the negative 2 meters, all divided by 2 times our potential difference of 4.1 times 10 to the 5 volts, again we only care about the magnitude, times Q, which is for an electron 1.602 times 10 to the negative 19 coulombs. And if you plug that into your calculator, you'll get an answer of 1.09 times 10 to the negative 4 meters, which is also equal to 1.09 times 10 to the negative 2 centimeters. And if we do some unit analysis, we have kilograms times meters per second squared times meters divided by volts times coulombs. This is equal to kilograms meters cubed divided by seconds squared. A volt is a joule per coulomb, so joule per coulomb times coulomb is just joules. A joule is a Newton meter, so this is a Newton meter, equal to kilograms meters cubed per second squared. A Newton is a kilogram, meter per second squared times meter. So this second squared cancels with this second squared. These 2 meters cancel with 2 of these meters. Kilogram cancels with kilogram, and so we're left with 1 meter at the end. Alright, for our second problem, we have an electron that's launched with initial speed 5 times 10 to the 6 meters per second, perpendicularly into a downwards uniform electric field between 2 parallel plates. The electron enters midway between the plates, which are separated by 1 centimeter and have lengths of 2 centimeters. If the electron is just barely able to get past, we want to find the potential difference between the plates as well as the field's magnitude. So, we have 2 parallel plates that have a uniform electric field going downwards. That tells us that the top plate is the most positive. The bottom plate is less positive, or we'll just call that negative. The separation between the 2 plates is r equals 1 centimeter, and the total length is 2 centimeters. And we have an electron that's entering midway between the plates, so this separation is 0.5 centimeters, and it barely gets past the plates. So if we consider the free body diagram of the electron, since the electric field is going downwards, the electron feels a force in the opposite direction since it's negatively charged, so upwards. We know that the net force is equal to F is equal to ma. So Fe is equal to ma. Fe is equal to Eq, so A is equal to Eq divided by m. We know that the potential difference is equal to E times the total separation between the 2 plates, R. So the potential difference, the total potential difference between the 2 plates, because we're referring to the electrical field between the 2 plates. So the electrical field is given by delta V, divided by R. So A is equal to delta V times Q divided by M divided by R. And this is upwards. So since the electron is going to be accelerating upwards, but maintaining its velocity in the x direction, its trajectory looks something like this, where since it barely gets past, we can assume that it skims the top plate. And so this is looking very similar to a projectile motion problem, so we'll set it up in a similar way, where we have our x components and our y components. In x, we have Vx equals 5 times 10 to the 6 meters per second, and delta dx is equal to this full length of 2 centimeters, since you can consider this point as when the projectile touches the ground. Of course, our reference is up as positive and to the right as positive. In the y component, we have delta dy is equal to 0.5 centimeters. Vy1 is equal to 0, and Ay is equal to delta Vq divided by Mr. And we want to solve for this delta V. And in order to do so, we know that the delta t between the x component and the y component has to be shared. It's the same amount of time. For x, delta t is equal to delta dx, or the displacement divided by the velocity. Meters divided by meters per second gives you seconds. For the y component, we'll have to use one of our kinematic formulas. Delta dy is equal to Vy1 delta t plus 1/2 Ay delta t squared. Since Vy1 is equal to 0, this reduces to 0. And if we isolate for Ay is equal to 2 times delta dy divided by delta t squared. We know what delta t is. That's equal to delta dx divided by Vx, and Ay is equal to Vq divided by Mr. And so Vq divided by Mr is equal to 2 times delta dy divided by delta dx squared over Vx squared. If we isolate for delta V, delta V is equal to 2 times delta dy times Mr divided by Q, and we can flip that fraction at the bottom since we're simply going to square it and then bring the Vx to the top, keep the dx at the bottom. So delta d squared x and V squared x. So if we substitute in, we get 2 times delta dy is 0.5 centimeters, or 0.5 times 10 to the negative 2 meters. M for an electron is 9.31 times, or 9.1 rather, 9.1 times 10 to the negative 31 kilograms. R, which is our separation, is 1 centimeter, or 1 times 10 to the negative 2 meters. And we're running out of room, so Vx is equal to our initial velocity of 5 times 10 to the 6 meters per second squared, all divided by Q, which for an electron is 1.602 times 10 to the negative 19 coulombs, divided by delta dx, which is 2 centimeters, or 2 times 10 to the negative 2 meters squared. And if you plug this into your calculator, you get an answer of 35 times 35.108 volts. So that's our potential difference between the two plates. And I encourage you to do the unit analysis. In terms of the magnitude for the field, we know that E, or rather delta V, between the two plates is equal to the electrical field times the separation of the two plates. And so E in magnitude is equal to delta V divided by R, which is equal to 35.108 volts divided by R, which is 1 centimeter, or 1 times 10 to the negative 2 meters, which is equal to, if you plug that into your calculator, 3510.8 volts per meter. Volts per meter is the same thing as 3510.8 newtons per coulomb. And so the potential difference between the two plates is 35.108 volts, and the electrical field between them is 3,510.8 newtons per coulomb.